This section is about exponential growth and decay. Our goal is to understand exponential functions and consequences of constant percentage change. Example 1. Suppose there are initially 2,000 bacteria in a petri dish, and the population doubles every hour. Is the population size a linear function of time? Let's examine our table. The number of bacteria was initially 2,000. Since it doubles every hour, after 1 hour, the number of bacteria is 4,000. After 2 hours, the number of bacteria is 8,000. Notice, during the first hour, we added 2,000 bacteria, but during the second hour, we added 4,000 bacteria. Therefore, the growth rate is not constant, so the function is not linear. However, the number of bacteria is increasing by a constant percentage rate of 100% each hour. 100% is the percentage increase because we added 2,000, or 100% of what we had the first hour, and 4,000, or 100% of what we had the second hour. In general, to get the next function value, we add 100% of the previous function value. A function that changes at a constant percentage rate is called an exponential function. Let's rewrite the table in a way that will help us find a formula for the number of bacteria in T hours. Recall, initially there were 2,000 bacteria in the petri dish. Each hour, the number of bacteria doubled. So after 1 hour, there were 2,000 times 2, or 4,000 bacteria in the petri dish. After another hour, we double that number again. We get 2,000 times 2 times another 2, or 8,000 bacteria in the petri dish. After another hour, we will again double that number. This time, we have 2,000 times 2 times 2 times another 2, or 16,000 bacteria in the petri dish. Notice, the number of bacteria in a petri dish in a given hour is 2,000 times several 2's. In fact, the number of 2's we multiply matches the number of hours since we initially put the bacteria in the petri dish. This means after T hours, there are 2,000 times 2 to the T bacteria in the petri dish. For example, find the population of bacteria 4.5 hours after the experiment described above began. To make this calculation, we will use the formula above and put 4.5 in for T. We get N, or the number of bacteria after 4.5 hours, equals 2,000 times 2 to the 4.5. Using our calculator, we get this to be approximately 45,255 bacteria. Note that the general formula for an exponential function is n equals the initial value, in our example it was 2,000, times base to the t. In our example, the base was 2. In general, the base is the number you multiply the current value of the dependent variable by in order to find the next value of the dependent variable.